This way. Okay, so we'll talk about topological chaos with set-oriented methods.
Okay, thank you. All right, now that I think my computer and the projector are talking to each other, so I'm going to tell you a little bit more about this connection with the Thurston-Nielsen classification theorem and how we can use that in looking at fluid stirring. There was a comment yesterday about mathematicians, applied mathematicians, physicists, and then other. And I actually sort of fit within that other here, where I'm in the engineering, science, and mechanics department. I better plug in now my director here. Okay. This has involved work with a number of people, of course. Excuse me. So Shane Ross is a dynamicist at Virginia Tech, with whom I'm working with on these set-oriented approaches. Piyush Grover was his graduate student who I worked with as well, and Mohsen Gesaria and Pankaj Kumar were two graduate students who have worked with me. I've worked for a number of years, as many of you know, with Hassan, and it was the time that he and Phil had spent together, where Phil was a mathematician in residence at the University of Illinois, where I had the good fortune of being a graduate student under Hassan at that time and got involved in this work at that point. And also a number of conversations over the years with Jean-Luc. And then there are several other people who have been involved, but not directly with the things that I'm going to tell you today. So this is a picture that you've seen a few times now, and I'm going to show you again at least once more. And the objective that I'm going to think about today is how to connect that, in some sense, very simple stirring flow of Stokes flow, how to connect that with some more realistic problems in the same vein as what Jean-Luc was showing with looking at the floats in the Labrador Sea. I'm not actually going to make quite the full connection. So this is a simulation of the oil spill off the Gulf of Mexico that I snagged from Maria off the web. I'm not going to go quite that far. I'm going to instead look at lid-driven cavity flow, where there are no stirring rods inside the flow, but by imposing velocities on the boundaries, we can look at a stirring inside. So what this is actually showing you right here is much of what I'm going to tell you today. So an overview of what we're going to cover. This first part, obviously, I'll be able to go through somewhat quickly, unless you happen to fall asleep during every other presentation of it so far, and then chances of you staying awake during my presentation of it are slim to none as well. I'm going to introduce to you this flow protocol that I have spent now a number of years thinking about. It looks kind of like a double gyre flow. Introduce you to almost invariant sets and set-oriented methods if you're not familiar with those, and how we can use those almost cyclic sets to identify some structure in the flow and use that to look at topological chaos or braiding in a lid-driven cavity flow. So here again is the Stremler interpretation of this braiding and stirring with use of the Thurston-Nielsen classification theorem. So we have a two-dimensional domain, punctured disk, and our punctures we generally think of as stirring rods, but I'm not going to have stirring rods in there, so they really are punctures that in many cases we think of as surrounding periodic orbits in the flow, and I'm going to try to extend that a little bit. So in terms of strict application of the theorem, we need these stirrers to move on periodic orbits. And we have, typically how we think about this is that these stirrer motions are generating a diffeomorphism on the disk. The perspective that I'm going to take is a little bit different from that. I'm going to have a diffeomorphism on the disk that happen to generate the stirrer motions. And part of the question I'm going to ask is, how do perturbations of this diffeomorphism affect the underlying topology then? And I'm going to use the idea of braids in order to help us visualize what's going on. Okay, so the Thurston-Nielsen classification theorem, again. So we're looking here at pseudo-Anosov type motions. And Jean-Luc talked about how reducible really isn't that interesting. Actually, most of what I'm going to show you is reducible, but it's reducible to something that is pseudo-Anosov, so we don't really need to talk too much about reducible. Okay, so the idea here is, again, that we're focusing in on this Thurston-Nielsen representative here, this mapping or diffeomorphism or homeomorphism here, where it has all these very nice properties given by the Thurston-Nielsen classification theorem, and we're wanting to connect that to a real fluid motion through isotopy, and then make predictions about what's happening in this real fluid motion based on what we know exists in this ideal representative. Okay, so this idea of isotopy, again, so the basic idea of isotopy from the perspective of fluid motion is that if we could get exactly the same result by holding all of the boundaries fixed in space, but maybe rotating them around each other, and then apply some arbitrary pressure distribution to the surface of this fluid, or even reach into each individual fluid particle and sort of shove it around wherever we want without breaking the continuity of the fluid, of course, but then shove it around. However, if we could achieve that same stirring motion by this magical pressure distribution, then that stirring motion is isotopic to the identity. Okay? So the only things that have any complication that are of interest from the topological point of view require us to move the stirrers around each other in enough of a complicated way that once we fix the stirrers in place, we can't push the fluid back to where we started from using some arbitrary pressure distribution. Okay? So we have this idea of isotopy that connects these different stirring motions, and the real power in applying this to a fluid, as Jean-Luc pointed out, is Handel's isotopy stability theorem, which says that these complex dynamics that exist in this idealized map or diffeomorphism from the Thurston-Nielsen representative, those remain under isotopy. It can only get more complicated. So if we look at the growth rate of material lines or the log of that growth rate, the topological entropy, then that really provides a lower bound on what's happening in our real fluid. Because this is from a topological point of view, of course, it doesn't give us any indication about the size of the measure on which this applies. So in practice, we could end up with a fluid motion where we get very large growth rates, but it's isolated right around the moving boundaries. And then the rest of the fluid just kind of sits there. And in the picture, which is probably coming, yes, here again. So you see that here, where at least over the finite time on which this experiment's been done, you don't see the exponential growth of this material line out here towards the boundary. And there are also some other physical arguments for how these fixed boundaries really slow down what's going on with the growth rate. One of the things that we didn't necessarily know was going to happen at the beginning when we first decided to do this Stokes flow experiment, we didn't necessarily know how much of the fluid would experience this exponential growth rate. And we were quite pleased to see that it does take up a sizable part of the fluid domain and has some realistic application to what's going on. Sort of the metric length of this does have some indication, or it does have some real connection to what's going on with the topological length of these lines.
If the boundary was closer, would the mixing region shrink, or
it would, in some sense, shrink, yes. And until it gets out closer to the boundary, it doesn't necessarily see that the boundary is there. So if you move the boundary in a little bit here, that probably isn't enough of a perturbation to affect what's going on here. But if you move the boundary in much closer, then it does have a strong effect on what's going on. So
mixed region continues to grow slowly.
Yes, so this mixed region continues to grow, but it grows slower and slower as it ends up getting close to the boundary.
Yeah, in other words, the mixing region is the whole domain in this case. And it's just a pattern. The dye hasn't yet visited the whole mixing region.
Yes, and the effect...
The section for this is dots everywhere.
Yes, that's true. That's true. It's just that you don't automatically see everything right away, and the amount of time that it takes you to actually approach the boundary with this mixing pattern slows down as you approach the boundary. Okay, so this is the protocol, and the reason I bring it up again is because I want to actually mimic this now without putting any solid rods into the fluid. So we first move these right two rods on a clockwise orbit until they've exchanged, and then we move the left two rods on a counterclockwise orbit until they've exchanged, and then we just repeat that pattern ad nauseum. Right? Or in this case, only 6. And here we have, as time going up, the braid representation of sigma 2, sigma 1 inverse. Okay? And so here we have the golden ratio that shows up, and the logarithm of that, this topological entropy here, so of 0.962, this is a number that we'll keep coming back to. And so we look at these essential curves, or these non-trivial material lines, and so they'll grow like lambda to the n here. And so we're going to look at one of the things we're going to look at is the connection between this topological growth rate and the metric growth rate. Okay, here's a picture. Okay, so how do we want to achieve this without putting any rods in the fluid? So this is a flow protocol that we'll look at. It's periodic in the horizontal direction with fixed boundaries on the top and bottom. And we impose a velocity on these top and bottom boundaries in a way that produces a flow that I would like. Okay. I'm going to assume that it's Stokes flow. One of the motivations for this came about from looking first at 2D lid-driven cavity flow. Here, there's just steady or periodic forcing on the top. It's uniform velocity imposed on the top or bottom of these boundaries. So this is the classic work by Julio Otino. And there was some more recent work, a paper that's been highly cited in terms of microfluidic mixing that Abe Struck published in Science in 2002, where he has this herringbone pattern on one of the walls of this channel. And the idea is as the fluid moves in this channel here and passes over these grooves, there's less resistance for the fluid to move along the grooves than across the grooves, and so you generate these counter-rotating patterns in a cross-section of this channel, and so they showed how you get nice mixing that occurs due to some stretching and folding of the fluid. They didn't explicitly show that this had anything to do with chaos, but they speculated that it did. Abe then went on to have a numerical model, an analytical model that then he did some numerics with that's closely related to the one that I'm showing here. There are some approximations he had to make that we get away from by assuming that ours is periodic in the horizontal direction. So then if you do actually an experiment with something that looks periodic in the horizontal direction, you put these surface grooves on and just a large number of them across a very wide channel, you find that the velocity distribution at the surface here along the groove looks a lot like a sine wave. So there's some physical motivation here for assuming that we have some combination of sine waves that are giving us our velocity distribution on the top and bottom wall. So I'm going to assume a stream function of this form, where for the double gyre flow, you assume that the f's here are just other sines or cosines. But in this case, we want this to satisfy Stokes flow, and so then you get an ODE for f. You apply the boundary conditions, and you find that you get an exact solution here. Okay. So we can take an infinite number of these. I mean, it's just a Fourier series representation for this lid-driven cavity flow, but I don't want to do that. I just want to take the first two modes, and in that case, we just have one large counter-rotating region or two equally sized counter-rotating regions here, and just add these together in a way that produces a flow that looks like this. And one of the reasons for doing that is the motivation is to have something that looks like a fixed rod that sits here, and then two rods that are exchanging their positions after some finite period of time. And then I want to flip things back and forth so that I produce a braiding motion that looks like this stirring rod protocol. So I have to have a very specific set of parameters here. So beta, it relates the strength of these two modes. So for a very specific value of beta, then I have this stagnation point here, or fixed point here, lying symmetric to a point over here that lies on the same streamline as the point that goes exactly through the center of the domain. Okay, very carefully constructed, obviously. And then we flip that we blink that in time in order to produce a stirring motion. It seems very contrived, I know, and it is. But one of the things I want to look at is what happens now if it's not exactly the way we want it. Okay. So the idea here that one of the things that Jean-Luc mentioned, this idea of designing for chaos, where we're trying to build a system where we know that there's a braid embedded in the flow, and that allows us then to ideally mix in some optimized way, although there is the question is really, what does this have to do with optimal mixing? That is still an open question. So with this appropriate choice of parameters, we can get these two different flow, these mirror flows here that we can blink back and forth between. And then if we choose the scaling just right and choose the time period just correctly, then these 2 points exchange position exactly after tau was 0.5. So the period of 1, we get first this point sitting here, and then it moves to the center. This point over here moves to the center, and then moves over here. So we can see that this gives us this braiding protocol that we're looking for. Okay, so this isn't necessarily anything new in terms of stirring with orbits in the flow. So one of the things that Jean-Luc has done is looking at this situation where we take one rod in a circular domain and move it on an epicyclic trajectory. And this one rod by itself produces a trivial braid, a braid on one strand. But if you look at stretching of a material line in this domain, it's clear that there is exponential stretching going on with this material line. And you can also identify here clearly one fixed point or region of elliptic island here in the flow. It turns out that there is another fixed point in this flow. And so this epicyclic trajectory is moving around what appears to be sort of rods in the flow. And if you look at these ghost rods and include those in the calculation of the braid, then you get a pseudo-on-off braid. You can calculate the topological entropy predicted by that topological braid, and it gives a good representation of what's going on in this flow. And then you can go a step further and actually put in fixed rods in the same, essentially the same locations. Was it exactly the same locations? I don't remember either. But put fixed rods where these fixed points sit, and then do the same stirring, and you see very much the same picture. Obviously now those no-slip boundary conditions generate some more complexity in the flow, and you get these other additional wiggles. But this is the idea of looking at the ghost rods, or just punctures in the domain, as equivalent to fixed rods or stirring rods in the domain. Okay, so here for this lid-driven flow with these very special choices of parameters, we have here 3 periodic orbits in the flow. And now if we apply this flow protocol after 1, 2, 3, 6 iterations of this, you can clearly see the exponential stretching. And one of the very nice things about this flow, we have imposed velocities on the top and bottom. We have slip boundaries on the side. And we can see that because of the way that those boundary conditions play in the dynamics of this flow, that the stretching extends up to the boundaries very quickly, and we get very nice filling of the domain very, very rapidly. Okay? One of the results of that is if you look at the actual stretching of a line in this flow, so the Thurston-Nielsen prediction here is 0.962, etc. The actual stretching in the flow gives a metric topological entropy here for the flow, 0.964. So this is a very sharp lower bound in this case.
How do you determine that?
Just numeric, this one? Yeah, so put some line, in fact, lines like this, and just stretch them. And then look at the asymptotic growth of those lines. Okay. So of course it makes a little bit of difference which lines you choose, but eventually they all end up giving the same, as long as they're essential lines, then they give you the same estimate. And you can look at sort of statistics of how good an estimate this is. And we really can only say up to this digit here because of that. Okay, great. That's all fine and dandy, but what happens if you are a little bit off from these exact numbers? And in particular, what if we have some general system where we kind of see regions that appear to be moving around each other, but we may not be able to identify exactly periodic orbits on which to place this Thurston-Nielsen classification theorem. Okay, so in this case, all of what I've shown you for this system depends explicitly on the underlying dynamics of that flow. So how can we perturb? There are a couple of different ways to perturb. One is to perturb the relative strength of these two modes, which amounts to changing the location of this separating streamline here. The other is to just change the amount of time that we allow this to run for, so we allow for the sort of overshooting of the position or undershooting of the exchange of these positions. They're very closely related. I'll show you what happens to that somewhat briefly here. Okay, so change the relative strength of these two, so I'm increasing beta by approximately 0.1%. And if we zoom in here, one of the reasons that we might expect something interesting to happen here is in the exact case that I showed you, we just have this one periodic, or period 3 orbit, and it's a parabolic orbit. So we expect it to be unstable to perturbations in the system. As you change beta in this way, the structure perturbs into two elliptic islands and two hyperbolic points, and we get what looks very much like a rod now that sits in the fluid. Of course, these two hyperbolic points, we don't expect them to exactly connect. We expect actually to have some very small homoclinic tangle there. But if you look at what the streamlines are for a cylinder in Stokes flow, I mean, it looks a lot like a cylinder. So we can see that the idea of having this be a rod that appears to be stirring the fluid makes a lot of sense. Okay, so what happens in particular with the topological entropy as we do these perturbations? Okay, so we're changing this relative strength. Here's the case that I just showed you. So this is this critical case, say beta star, and this is the topological entropy that's predicted by the Thurston-Nielsen classification theorem. And we see this region around this value of beta where it's well represented by what the theorem predicts. If we decrease too far, we can see this incomplete exchange of these points, and we don't get as much stirring as you would want. If we go too far to the right, then what we end up here is with a lot of extra stretching and folding that occurs in this system, and that just gets worse. Okay. As you increase, you see these elliptic islands that can act like ghost rods. So that's fine as far as applying the theory goes. We just have perturbed locations of where these are. I mean, you can think of this as a braid actually on 30 strands that's reducible to a pseudo-Anosov braid that's still on 3 strands, because all of that these strands do is wrap around each other, twist around each other as the flow goes along. And eventually, that structure is destroyed, but I'm not going to look at that complexity. I'm actually interested in what goes on in the other direction, and it turns out from the numerical point of view, it's easier to just perturb in tau. All this is to show you is that the same sort of thing happens. So if instead you allow the points to exchange a little bit further than the ideal case, then you get this rod-like structure that shows up again, and you get more stretching than in this sort of ideal case. But as you reduce below, you still maintain this level of stretching, even though there are no longer any low-order periodic orbits that exist in the flow. Okay? I could show the Poincare section, but it's just a complete chaotic sea. There are a few periodic orbits that exist in this flow, or fixed points in the flow. I mean, there are some corners in the domain. There might be some things that are going on far away from the center, but they're not doing any braiding. Okay, and so it's interesting to say, okay, this is a region where the TN classification theorem doesn't strictly hold, but there's this shadow of the dynamics that exists. That can we somehow capture that? And so one way to look at this is to use a set-oriented method. So this is the idea of almost invariant sets. Basically, there are regions of phase space that stick together for a significant period of time. And this is something that Michael Dulnitz and Gary Froyland have been working on for over a decade, and looking at how that connects to the Perron-Frobenius operator, and you're looking at the eigenspectrum of the Perron-Frobenius operator, and it's also related to this idea of the strange eigenmode. There's the mixing matrix that's been used as another way to look at this. Igor Mezich has looked at the Koopman operator, which is intimately related to this same idea. So from the point of view that we're interested in, of looking at regions of the fluid that sort of stick together, and you could consider as rods that are moving the rest of the fluid around, so to say. Here, for example, is a calculation of almost invariant set on one of the poles, in the atmosphere on one of the poles. It's connected to Lagrangian coherent structures, which we heard a little bit about earlier, which these are sort of the complex dynamics equivalent of invariant manifolds of the flow, and they sort of wrap around on the boundaries of what looks sort of like elliptic islands, but in a much more complicated sense. Okay. We look at a discretized approximation to the Perron-Frobenius operator. This is the standard way to approach this, is just to partition the domain into a number of boxes and look at the transition of one box to the other boxes and how that's distributed among the boxes, generate a matrix. Okay, so we have this transition matrix, and then we look at the eigenspectrum of that transition matrix. So for the case that we're looking at, we're actually able to reversibilize this transition matrix so that the eigenvalues are all real, which you don't have to do. You can actually look at complex eigenvalues and then talk about periodicity, but I don't want to get into that. The basic idea is that you look at the measure of the intersection between some box BI, let's say it's this one right here, with the mapping of some other box BJ. So the classic definition is to map backward. Okay, so we look at BJ, and then under these two iterations that make one full period of the flow, we look and see where that box ended up, and we look at the intersection of that with this box BI, and so that gives us the ijth component of P, normalized by the measure of BI. And then it's actually really hard to do this in terms of the full volume, so really we just seed this box with a number of points, and then we just count the number of points that end up in box BI. Okay. And this is an example of what you get out of that. The first eigenvalue that you get and its corresponding eigenvector should be 1. So in this case, it's approximately 1 just due to limitations in the numerics. That's because this whole space is an invariant. Okay, and so we just say the space maps to itself. So really what's interesting is to look at the second eigenvalue and on. And everything is ordered by a decreasing value of the eigenvalue. Okay. And in particular, we're going to focus in here on the second one, at least to start with. Okay. So this is a visualization of the eigenvector. Okay. So we have most of the eigenvector sits in these locations here. So it's an eigenvector in the sense that we just number the boxes, say from 1 to, in this case, about 19,000. Okay, so that gives us a vector on this space, and the value of the individual components are what generate this color plot here. Okay, so what we get here, what we look for here is the zero contour. It's approximately the zero contour. You actually have to play with that value a little bit. And the zero contour separates the domain into almost invariant regions. And in this case, we have two almost invariant regions. The one region that corresponds to these three red areas, and then its complement. Okay.
Mark, this is for perimeter value, it's just below where the orbits stop.
Oh, yes. So this is for, and we can look at tau as 1. We can actually look at any value of tau and get at least in the neighborhood of tau is equal to 1, get a similar picture. But yeah, this is, so thanks, Jean-Luc. This is a case where there are no periodic orbits in this flow.
Of low period, sorry.
Yes. Any interesting low-order periodic orbits that braid. Yes. If we go down in the eigenspectrum, in this case we see some very similar structure. What's happening here is that the zero contour sort of lies somewhere out here in the green. And so we see that in this case, particles that start close to where the periodic orbit used to be stay there for a very long time, or near the others. Because it's a periodic orbit, they just sort of bounce around between these three regions. In this case, it shows that they actually stay on one side or the other. But this is, the ordering of this eigenvalue actually gives us an indication of how leaky this is. It's not invariant, it's almost invariant. And the smaller the eigenvalue, the more leaky it is. So the tendency to cross back and forth within one of these regions, there's a higher probability of that than of the particles actually leaving this region. Okay, okay, so as far as almost invariant sets, really what that's looking at is just the map. And it's just saying that particles within this region don't leave this region. They might be anywhere within these three regions right here, but under that map. It doesn't really tell us anything about braiding yet. So we extend this. I might need to get some water, although I'm almost out of time.
Behind you.
All right, make sure I last another 5 minutes. Okay, so yeah, I've said some of this already, but what turns out is that because of the fact that particles move between these three regions, we can think of them not just as almost invariant sets that are fixed in space, but as almost cyclic sets where particles tend to move from one to the other, but they're almost cyclic in the sense that eventually they leak out because there aren't periodic orbits, period 3 orbits that exist here. So particles will come in, spend a very long time around here, and then leave. Okay.
It's like Harman's diffusion. Leaky barrier.
Yeah, yes. And in fact, well, so you can't really look at, say, a diffusion across, say, an invariant manifold in this case, because there are no periodic orbits in the region here. But yes, I mean, it is slow diffusion across sort of a boundary in this case. You can generalize this to aperiodic systems, but it involves a lot more work than just looking at the Cohen-Frobenius operator or approximations of it. But one of the ways to visualize this is now to vary the start time of where we consider to be time 0 in generating this matrix. Okay? And we can look at how that varies. This is for a bit lower value of tau. Okay, there we go. And that's how this movie was generated. It's looking at the almost cyclic sets with the initial time parameterized to show you if we start at a different time, where do these sets sit in space. Okay? And you can look at the braid that's generated by those. Okay? So these produce the ACS. So if we're not now thinking about particle trajectories, but just the almost cyclic sets that come from the particle trajectories, they generate this same pseudo-Anosov braid as the rod stirring protocol. The hand-waving part of this is that the particle trajectories do not really follow these ACS for all time. Okay? They eventually leave those trajectories. But the reason why this still works well is that if you're looking at exponential stretching of material lines, if you can go for 10 periods and actually compute things for 10 periods, you're actually doing really well. I mean, exponential stretching over 10 periods is huge, okay? And the ACS are defined in a way that the particles tend to stay around these for at least 10, 20 periods. So over the time in which we're interested in the exponential stretching, the particles are well represented. So you can think of the particle trajectories as really an aperiodic braid. And that section of the braid that we're calculating right now is well approximated by a periodic continuation of that section in time. Okay? Just very briefly, what happens to that structure? I've shown you the structure where we get 3 strands in the braid for very small perturbations in tau. As we decrease tau much more significantly now, we get a breakup in this structure. Okay? And it breaks up in various ways that if you're interested in this, I can tell you about. And I'm not going to really discuss the crossings here. We're choosing to follow the eigenvector that gives us the best braid representation. Okay. So I'm tweaking it a little bit. For one of these cases, say we get a braid on 13 strands. We can look at the braid on 13 strands. We can use Toby Hall's code in order to compute what the topological entropy is predicted here from the Thurston-Nielsen classification theorem. And then we can look at, this is the entropy given by actually following a material line in the flow that I had shown you before. This is what's predicted by the Thurston-Nielsen classification theorem based on the number of strands in the braid. So when we have a breakup from 3 strands, first we go to 16 strands, the entropy drops slightly. From 16 to 13 strands, the entropy drops again, and it just keeps dropping as we change the number of strands. And in every case, that's giving us a good lower bound on what's actually happening in the flow. Okay? So to summarize, so we have these almost invariant sets. We look at the motion of these almost invariant sets or almost cyclic sets around each other, associate that with the braid. We can generalize this to aperiodic flows if we would like, and that's something that we're looking at doing. So we take the topological properties of this braid based on the almost cyclic sets, and then from that we infer things about the dynamics, the stretching of the fluid. So then we can make, if the orbits are exactly periodic, or if these were invariant sets as opposed to almost invariant sets, then we can say very concrete, come to very concrete conclusions based on the Thurston-Nielsen classification theorem. But it's clear from what we've looked at thus far that as long as these sets aren't too leaky, they give a good indication of a connection between the dynamics of the flow and what we see in the Thurston-Nielsen classification theorem. Okay. And one of the things that would be interesting to pursue a little bit further is if we just look at the eigenspectrum and then try to say, okay, but there's some bifurcation in the eigenspectrum. What does that mean about the topology and how the underlying flow is being stirred? So instead of trying to go in and look at the dynamics of the flow itself, to look at bifurcations in the eigenspectrum, and that might give us some indication about changes in behavior that are worth pursuing. Okay. And then outlook, much of what Jean-Luc mentioned as well. So there's still some work to do on connecting this with actual fluid mixing. 3 dimensions, you can fake it to a certain extent. So if you take this lid-driven cavity flow and then impose an axial Poiseuille flow on top of that, that's close enough, in a steady flow, that's close enough to a 2+1 dimensional space that you can look at braiding in that case, and then it works. Okay. And then how does this relate to real data? We saw in Jean-Luc's case where you can take floats and look at braiding in floats. This would be, say, an alternative view where we're trying to look at approximations for invariant regions or almost invariant regions And how can we use that then to apply some of these very powerful topological tools to messy dynamical systems?
Thank you very much. Questions?
May I ask, is it the notion of topological entropy is a bit similar to the notion of metric entropy, which is related to the sum of Lyapunov exponents?
They're related. The topological entropy is always going to be larger than the metric entropy. Did I get that backwards?
Yeah, so the variation
Yes.
principle, so the topological entropy is the supremum of the metric entropy over all ergodic mixes. So if you have positive topological
Yes.
entropies, you have measures with positive entropy.
Right. And really what happens there is that the topological entropy is just measuring, sort of from the physical point of view, it's measuring the growth rate of material lines, and that is going to be dominated by regions. So say the stretching in the domain is non-uniform. It's going to be dominated by the regions where the stretching is large, where the metric entropy, you're spending time both in the regions where there's large stretching and then spending time in regions where there's low stretching. It averages those out in a very different way than the topological entropy does.
This leaky barrier, what is the effect of that on the line length growth? Does the line length grow intermittently or it grows slower?
Are you asking as the barrier becomes more or less leaky?
Yeah. Well, it's leaky, noticeably leaky.
So so we're looking at defining this where it's almost invariant. So more leaky or less leaky, it's still a barrier in the flow. It just might not be a barrier for very long. If it's too leaky, then it's not. There's really not anything there. Material just passes through it, and it's not enough to snag the fluid. But if we're looking at these almost invariant regions, so over the number of periods that we're interested in doing this stretching, they look like a barrier in the flow, then the leakiness from the point of the line stretching doesn't have a whole lot of effect. Okay, because it's snagging, you can think of it as snagging the material line and dragging it along. Okay.
You used a switching protocol in
Yes.
the fluid motion. Presumably, if you made it sinusoidal instead, it really
not.
wouldn't change anything, would it?
No, it shouldn't change it. It'll change the details of dynamics.
Yeah, sure.
But presumably you can still choose these
Yes.
parameters in a way
Yes.
so you can still build up these periodic orbits. Yeah.
Can I just offer a quick comment on Conrad's? I think,
Can you speak loudly, please, John? Can you speak loudly?
okay, maybe one interpretation of the leaky barriers is that it's like having a tachypolar where once in a while the line slips and doesn't catch on to one of the rods, right? So that's why you're getting a lower stretching when there's leaky barriers, because it's trying to do the same thing as the tachypolar, but because it's leaky, sometimes the line goes through and shortens. So I think that's kind of what happens. That's it.
Yeah, although it doesn't
Unideal
it
tachypolar.
doesn't do it in sort of an extreme way. It's more like they're porous barriers where it's sort of just it slips through the barrier and it's not a catastrophic event. And so it's still snagging it, but it may not snag it quite as far. So you do see a slight drop in the topological entropy as they become more and more leaky, but it's not a very noticeable drop until you change the topology of these almost cyclic regions.
Question really was whether the drop in entropy is intermittent, is that thing, or is it just
Oh, no, it's not. So that's the red line here is the actual topological entropy for the flow. Okay, so that's not intermittent. It's this prediction or the lower bound that's given by the braid that's intermittent in this case. And some of the work that Jean-Luc has done or one of the things that he has said is that presumably, and maybe it wasn't you who said it first, which is why I seem to be stumbling right now, is that maybe it was Phil. So you should be able to find enough points in the flow that if you identify the right points and then compute the entropy based on those points, you should be able to approach what's actually going on in the flow. I mean, that's really what the entropy is. And if you come up with enough points and you're following that, and then you get this huge braid, you might actually be able to improve this bound. But what we're looking for here are low order, a low order description, so as few braids as as few strands as we can get in order to define this. And then there is this intermittency.
That's Qatar.
Okay.
Oh, yeah, okay.
Okay, I think we should wind up the questions. So let's all thank Mark again.